Section 10.2 Inferences for two population means. Here we're going to be dealing with two population means that are normally distributed. Out of these two populations, we're going to take a sample from each. Those two samples are going to be independent. That's a very important condition for us to use this. The standard deviation here for both of them, originally for this populations, call them sigma 1, sigma 2 are equal. I'm going to call it just sigma. But in this case, still we have sigma is unknown. Sigma is unknown. And so what we need to do here is we go through this written stuff here. It says x is the variable x is normally distributed for each of the following populations with the standard deviation equal. The independent sample sizes n1 and n2 for both of them. The variable t, that's the t distribution or t statistic here. We have two of them, x1 bar, x2 bar. These are the means for each sample. So for sample 1, it has a sample size of n1. S1 is the sample standard deviation, sample 1 standard deviation. And that's where it's coming from, mean 1, mean 2. Now SP, what is SP? SP is the, what we call it, pooled sample standard deviation. And it has a formula, you'll see it in a minute. Pooled because you're dealing with both of them, the S1 and S2 together. And what happened here is the degrees of freedom is different than what we have been using. It's going to be n1 plus n2 minus 2. So you n1 and n2, they don't have to be the same. They can be different. It's fine. And what are the assumptions first on this test here? We're going to call it the pooled t-test. And it's good to know if you decide to use the calculator, it's good to know this is called the pooled t-test. What do we have? 4 conditions of very important. The samples are simple random sampling. They're both independent, coming from a normal distributed population, or the size for each one is bigger than or equal to 30, and they have equal population standard deviation. Population equal. So sigma 1 equals sigma 2. That's important. So this setting here is the same as the previous section. This is the t value that I spoke about, and this is the SP. But notice this one here doesn't have mu1 minus mu2 as it was here, because when we set the null hypothesis, it's going to be mu1 equals mu2 all the time. An alternative hypothesis, it depends if it's going to be it does not equal or less or bigger. What matters is the first one here, to see from here, if you subtract mu2 on both sides, this equals 0, and that's why this part here is gone all the time, and that reduces the formula down to this one. So now we're going to learn how to find, we are going to learn how to find the t-statistic here, the t-statistic value based on the given alpha as well. We do need alpha. So we use the pooled t-test and the pooled t-interval. So we're going to learn both of them to conduct hypothesis testing. So let's look at an example first. Say for the first sample, they give us the mean 12, standard deviation 2.4, the sample size 13. And the next one, x2 bar, is 16, S2 is 2.3, N2 is 13. And let's say at alpha 0.10, we have, we're going to do, let's assume it's a two-tailed test. Okay, so let's find the t-statistic value. Of course, if you want to run a testing, hypothesis testing, you write mu1 equals mu2, and since it's a two-tailed test, we say that does not equal to. The t statistic value is x1 bar minus x2 bar over S sub P, P for pool, 1 over N1 plus 1 over N2. We have N1, N2, X1 bar, X2 bar, but we wouldn't have S sub P. So we do need to find S sub P. S sub P is given by the formula N minus 1, S1 square, N1 here, N2 minus 1, S2 square, divided by N1 plus N2 minus 2. So let's see how we find this out. Is the square root of N1. N1 is 13 minus 1. S1 is 2.4 square plus 13 minus 1, 2.3 square, all divided by 13 plus 13 minus 2. So then I calculate this on my calculator, it gives me 2.35. That's S sub P. Then we can go back to the formula for T sub 0. The T statistic is X1 was 12 given, X2 is given as 16, S sub P is just found it, the square root of 1 over 13 plus 1 over 13. And that gives me negative 4 over 2.35 square root of 2 over 13. Put that in the calculator, negative 4.340. Rounded to 3 decimal places. So that's how we find T sub 0. Now, if we need to find the other values, let's say like I want to find maybe the critical value. How do you find the critical value? How do you find the critical value from this? To find the critical value, because it's a two-tailed test, we find T sub alpha over 2, plus or minus. So plus or minus T, alpha is 0.10 over 2, 0.05, and degrees of freedom, it's N1 plus N2 minus 2. N1 is 13, N2 13 minus 2, 26 minus 2, 24. So now we are going to construct, after we find the Z value, so now use table 4 to find out with that degrees of freedom and this T, what would be the critical value. So the critical value that I found is 1.711. So this means you go 1.711 here, and by symmetry negative 1.711. So this and this. Now, where does the value of the T statistic value that we found here, that's a negative something, it's somewhere here, negative 4.340. That's T sub 0. So we say since the test statistic falls in the rejection region, we reject the null hypothesis. We reject the null hypothesis. Another thing we need to learn is the interval. The T interval, let's call it. How do we construct T interval? The T interval for the difference of mean 1, mean 2, how do you find that? Is x1 bar minus x2 bar plus or minus T sub alpha over 2 times SP, the square root of 1 over N1 plus 1 over N2. Almost everything is given here. What we need to do is x1 bar, that's the mean. It was given to us as 12, and this one is 16, plus or minus T sub alpha over 2. That's the one we found earlier. So if they say, they have to say like 90% confidence, let's say. So this means we know what T sub alpha over 2 is. So when we usually have usually have 1 minus alpha is the 90%. So 1 minus 0.90 is alpha. So alpha here is 0.10. So alpha over 2 is 0.05, the one we found earlier. So that falls under the same value, which is the 1.711 times S sub p. We found it earlier. What was S sub p? 2.35. The square root of 1 over 13 plus 1 over 13. And then what you can do, you can split this into two cases. This is -4, one time minus and one time plus. So minus 1.711 times 2.35, the square root of 2 over 13, or -4 plus 1.711 times 2.3, the square root of 2 over 13. And we can run some calculations on the calculator. This gives me about -5.577, and this is about -2.423. So the interval would go from -5.577 to -2.423 based on this information that we have. This is for two-tailed test. It works the same way for one-tailed test. It works the same for any other, like the left-tailed test or right-tailed test. It's the same concept. Let's look at another example for constructing confidence interval for the t interval or t confidence interval. Another example. Let's say sample 1 has a mean of 13.66. The N1 is 10, standard deviation is 4.33. So the data originally was given in a table, and then you need to count how many numbers in the table, and that was 10 for each one of them. But these numbers, the mean and standard deviation, were given to us. Sorry, that's not 10, that's 4.29. And the question is obtain 98% confidence interval for the difference of the population means. Okay, so same formula that I just used, we can follow exactly the same formula and see what we can get. So the first thing we have here is alpha, which is 1 minus 98%. That's 0.02 or 2%. Okay, that's alpha. But we want to find t of sub alpha over 2. That's a t of 0.02 divided by 2, t of 0.01. We need the degrees of freedom, n1 plus n2 minus 2, 10 plus 10, 10 plus 10, 20 minus 2 is 18. And what do we need to find? We need to find the interval. Always write down the formula. So it's x1 bar minus x2 bar plus or minus t sub alpha over 2 times s of p, the square root of 1 over n1 plus 1 over n2. So we do have n1 and n2. We do have x1 bar, x2 bar. What would be the value here? To do that, we go to table 4. So if you go to table 4, and then the degrees of freedom 18, and under that number, so in that column, I found it's 2.552. So far what we have this is given, this is given. The only thing is missing is S sub p. And S sub p, it has a formula to find it, S sub p. So what was the formula for S sub p? Well, S sub p is the square root of n1 minus 1 s1 square plus n2 minus 1 s2 square over n1 plus n2 minus 2. n1 was given 10 minus 1. s1 was 4.33 square. n2 is 10 minus 1. s2 is 4.29 square over n1 is 10 plus 10 minus 2. And we need to put all this into the calculator, see what we get. And that gave me about 4.310 if I round to 3 decimal places. So I found everything now. I can go back to x1 bar minus x2 bar plus or minus t sub alpha over 2 times s sub p, the square root of 1 over n1 plus 1 over n2. Let's substitute them in. x1 bar is 13.66. This is 18.47 plus or minus this one, t sub alpha over 2 was, we found earlier, 2.552 times SP, we just found it, square root of 1 over n1 is 10 and n2 is 10. So let's see what we get for the first one. So 13.66 minus 18.47, that's negative 4.81 plus or minus, we can multiply that together, 4.31, that's 10.99912, and this is 2 over 10. And now we need to split it up, one time positive, one time negative. So negative 4.81 minus 10.99912, 2 over 10, negative 4.81 plus 10.99912, square root of 2 over 10. So negative 4.81, 10.99912, square root of 2 over 10. So that's a negative 9.729. And this one, negative 4.81 plus 10.9992 times the square root of 2 over 10. That's 0.1089. If we need to round it, that would be 90 to 4 decimal places, or to 3 decimal places if we need just 90, like that. So the interval would be negative 9.729 to 0.109. So that's the interval.